Good evening everyone, good evening. I welcome you all again to the NEET Elite. Hope my army is doing great, having the good time. Yes. Well people, if I'm audible and visible to everyone, let me know in the chat box with a thumbs up. Let me know in the chat box with a thumbs up if I'm audible and visible to everyone right here. Welcome guys, welcome to the session, welcome to the session. Welcome to the session. Yes, welcome to the session. Yes. Lag in voice. Is that? Is everything perfect now? Just give me a second. Let me check it out. Is it perfect now? Am I audible and visible to everyone properly now? Yes. Yes, okay. Cool. Just a second, guys. Just a second. Wonderful. So, people, as you all must be knowing, today we are going to start a new chapter, which is of Class 12 Chemistry. The name of the chapter, as you all must be knowing, it's Chemical Kinetics, right? It's Chemical Kinetics. And in the today's session, we are going to understand the rates of the reactions. We are going to talk about the average rate of the reaction, instantaneous rate of the reaction. I'll be telling you how to write the rate of the reaction as per the stoichiometry. Then we'll go to the law of mass section, rate law, order, molecularity. Everything is going to be done in the tonight's session. Yes? So all of you must be super excited for it. Yes, if you're super duper excited for the session, let me know in the chat box. Yes, Chiranjeevi, after this we are going to start the atomic structure. Chill. Everything will be done and dusted. Yes. Wonderful. Yes, Manoj, I'll be giving you the schedule in the tomorrow session. Okay. Well, people, apart from this session, let me tell you, tomorrow at 11 a.m. Okay. Tomorrow at 11 a.m. I'm going to take one short session of the chapter electrochemistry, but not on this channel. That will be on Vedantu JEE English channel. Okay. All of you can join that at 11 a.m. sharp. Tomorrow at 11 a.m. I'm going to start electrochemistry one short series. That will be for 3 hours. In those 3 hours, we are going to finish the electrochemistry in Vedantu JEE English channel. So do attend that session as well, right? I'm doing wonderful, guys. I'm doing wonderful. So before starting the session, let me introduce myself. As you must be knowing now, my name is Wassim Sir and I'm your chemistry master teacher right here. Yes, Ashita, that's definitely going to be helpful for you. Yes, absolutely. Yes, indeed. Okay. So people, before starting the session, let me give you the brief introduction about the NEET 2021 crash course, which we are starting on the actual Vedantu platform. If you want me to personally train you in your chemistry, okay, if you want the teachers of your choice, right? If you want the teachers of your choice to train you personally for the upcoming NEET 2021, do get enrolled in this crash course wherein you get the benefit of doing that. Yes. And apart from the syllabus completion right here in this NEET 2021 crash course, there will be time management sessions. There will be sessions on the tricks and tips of how to solve the questions in lesser time. Not only about the syllabus completion, not only about the time management sessions, there will be a lot more than that. Regular test series and assignments will be provided to you. Yes, and at the same time, there will be mock tests by means of which you can compare your ranks with the other students throughout the country. Yes. Okay. So people, how to get enrolled in this crash course over here? Let me tell you, you just have to click on the Vedantu app. Okay. After clicking on the Vedantu app, just click on the NEET crash course. Okay, and use the coupon code as WSCC. On using this coupon code of WSCC, or maybe it can be WSCC21, you'll be getting some discount as well. Okay, and people, the crash course link is there in the description box, and as I tell in every session, batch starts from every Monday. On every Monday, we start a new batch. Okay, so do get enrolled in this crash course. You're definitely going to get benefited out of this. Okay, because if you see the Vedantu 2020 NEET selections, majority of the students were from this crash course batch, okay, which will be there on the actual Vedantu platform, right? Yes, okay. For the ones who have not liked the video yet, do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, okay? Yes? All right. Let me know in the chat box first if you are super duper excited about the today's session. Let me know in the chat box. Let me know in the chat box. Well, people, today we are going to learn the rate of reaction, law of mass action, rate law, elementary and complex reactions, molecularity, and the order. We are going to talk a lot today, yes, about the chemical kinetics. And majority of the discussion is going to be the theoretical discussion right here. Yeah? Good evening, everyone. Good evening, good evening. Welcome to the session. Welcome to the session, guys. Welcome to the session. Okay. Yeah, wonderful, guys. Great. I can see the Josh coming back into this channel. That's wonderful. That's great. That's actually great. Yes, Yashwant, I can see the army is back. Yeah? Wonderful. So, people, let's get started with something called as chemical kinetics, okay? Let me first of all tell you what this chemical kinetics is all about, right? But people, let me tell you, you guys are going to make the notes with me right here, okay? Whatever I'll be writing on the screen, whatever I'll be telling you, just make proper and clean notes of that, okay? Just make the notes crisp, right? Whatever I'll be writing on the screen, you are going to note that down with me right here, okay? All right, so we are going to start something called as chemical kinetics. Well, people, in this chemical kinetics, what all things we are going to talk about? Well, people, chemical kinetics is that branch of chemistry which deals with the study of the rates of the reactions. Number one, which deals with the study of the rates of the reaction, right? The factors which affect the rate of the reaction, and at the same time, the mechanism which will be involved in a chemical reaction. Right? So in the chemical kinetics chapter, we are going to talk about the rate of the reaction. We'll be talking about the factors which affect the rate of the reaction. We'll be talking about the mechanism of different reactions right here. People, you would have seen in your organic chemistry, a lot of reactions are there which are slow reactions. Some reactions are fast. Some reactions are moderate. In this chapter, you'll be getting to know why some reactions proceed slowly, why some reaction proceed fastly, why in some reactions the rates are moderate. All those things we'll be getting to know in this chapter in detail right here, okay? So the first point, the first thing which we are going to talk about right here, that's what we call as rate of reaction. That's what we call as rate of reaction. Now the point is, how do we define the rate of reaction right here? Okay, see guys, as per its simplest definition is concerned, rate of reaction is defined as, let me write it for you, rate of reaction is defined as change in the concentration. It is defined as change in the concentration of either reactants or products, of either reactants or products, of either reactants or products in a unit time. In a unit time. This is how we define the rate of the reaction. Yes? Okay. So as per the definition of rate of reaction is concerned, it is defined as change in the concentration of either reactants or products in a unit time. Right? How do we calculate it? Simply, guys, rate of reaction is nothing. It will be defined as change in the concentration of reactants or products, which I'm representing by delta C. Change in the concentration of reactants or products divided by time. Divided by time. This is how we calculate the rate of the reaction. Yes? Now people understand one important thing right here. The rate of the reaction which we are going to calculate right here, which is basically defined as the change in the concentration of reactants or products in a unit time, correct? We classify this rate of reaction into two types. One is called as average rate. One is called as average rate of reaction. One is called as instantaneous rate of reaction. I'm exactly starting from the basics, okay? People, the rate of reaction is classified into two types. One is called as average rate of reaction. One is called as instantaneous rate of reaction. What is this average rate of reaction all about? What is this instantaneous rate of reaction all about? That's what we'll be talking about in the beginning. Yes? Let me first of all tell you, average rate is represented by RAV, and instantaneous rate is simply represented by RINS. Yes? Okay, now the point is, what is this average rate of reaction all about? Then we'll be talking about the instantaneous rate. So first of all, we'll be talking about the average rate of the reaction, which I'm representing by RAV. Average rate of the reaction, which I'm representing by RAV. Now people, average rate of the reaction is defined as change in the concentration. Yes, I'm writing it right here. Change in the concentration of reactants or products in a given interval of time. In a given interval of time. Yes, in a given time interval. What do we mean by that, and what all things we need to remember from here? Understand properly what I'll say. Let's say I'm taking a general reaction like this, in which reactants are getting converted into products. Let's say this is the general reaction which I'm taking right here. Yes? Let's say guys, let's say at time t is equal to 0, the concentration of reactant is C1 molar. The concentration of product at time t is equal to 0 will be 0, because at time t is equal to 0, the reaction wouldn't have started. And if the reaction wouldn't have started, there will be 0 amount of product at time t is equal to 0. Yes? Now people, once the reaction starts proceeding in the forward direction, once the reactants start getting converted into products, what is going to happen to the concentration of reactants? Can I simply say concentration of reactants with time is going to decrease and the concentration of products with time is going to increase? Yes? Let's say at any time t1, the concentration of reactant left is C2 and the concentration of product formed is equal to C3. Yes? C1 is the concentration of reactant at time t is equal to 0. C2 is the concentration of reactant at time t1. C3 is the concentration of product at time t1 right here. Yes? Now people, if I want to define the average rate of the reaction, in the given time interval 0 to t1 right here, how will I be defining it? I can define it in two ways. Either I can define the average rate of reaction with respect to reactants, or I'll be defining it with respect to products. Yes? Absolutely. Now guys, understand. First thing, if I'll ask you, I'll say simply C2 is going to be less than C1. Do you agree with this? The concentration of reactant at time t1 is definitely going to be the concentration of reactant at time t is equal to 0. Absolutely. Now guys, I can write something like this. Average rate of reaction with respect to reactants. I can write it change in the concentration of reactant, which I'm representing by delta C. Change in the concentration of reactant divided by time interval, which is 0 to t1. Yes, divided by time interval, I'm writing t1 right here. t1 is the time interval, yeah? Absolutely. Now guys, what is the change in the concentration of reactant right here? Can I say it's going to be final concentration of reactant minus initial concentration of reactant, which is simply going to be C2 minus C1 divided by T1. This is going to be the average rate of the reaction with respect to reactants. Absolutely, yeah? Similarly, I can calculate the average rate of reaction with respect to products as well. It's going to be change in the concentration of products, which I'm representing by delta C, divided by same time interval, which is 0 to T1. So T1 is the time interval in which I'm calculating their average rate right here. Yes? Now guys, change in the concentration of products. Can I say it's going to be final concentration of product minus initial, right? C3 minus 0, which will be simply C3 divided by time interval T1 right here. Absolutely. So this is going to give me the rate of reaction with respect to reactants. This is going to give me the average rate of reaction with respect to products, right? Now people, the point is, how do we identify the rate of reaction is with respect to reactants or with respect to products? Understand one important thing right here. See guys, I told you the value of C1, the value of C2 is less than that of C1. If C2 is less than that of C1, can I say the value over here will be coming as negative? Can I say the value over here will be simply positive? This negative rate has a significance. First of all, as you all must be knowing, rate cannot be negative. Then how come this negative term comes over here? What all idea this negative term gives me over here? What is its physical significance? Whenever the rate of the reaction comes out to be negative, that means we have calculated the rate of the reaction with respect to reactants. And what does this negative sign signify? It simply signifies the concentration of reactant decreases with time. Yes, it simply signifies the concentration of reactant decreases with time. So first thing which you need to remember right here, what is that? Whenever the rate value will be coming as negative, which is not possible. So what this negative is all about? This negative simply tells you that you have calculated the rate of reaction with respect to reactants, and the meaning of this negative sign simply is that the concentration of reactant decreases with time. That's it. Yes. Now people, over here the rate of reaction comes out to be positive. What does that mean? Whenever the rate of reaction comes out to be positive, that actually means we have calculated the average rate of reaction with respect to products, and this positive sign signifies that the concentration of product increases with time. Yes, so this is all about the average rate of reaction. Very, very, very simple. Yes. Now people, one more thing right here. If I want you guys to tell me what can be the units of this rate right here. See guys, in the numerator term we have got concentration, in the denominator term we have got time. So the unit of concentration, as you all must be knowing, that's moles per liter divided by second. So the unit of rate of reaction is going to be simply moles per liter per second right here. It has got other units as well, which I'll be letting you know in some time. Yeah. Now guys, I'm going to make you understand the same thing right here graphically. I'm going to make you understand the same thing graphically right here, okay? I'm exactly starting from the basics as I told you, yeah? I'm exactly starting from the basics as I told you right here. See guys, let's say I'm plotting a curve between concentration versus time right here. Let's say I'm plotting a curve between concentration versus time right here. And as you all must be knowing, this point represents time t is equal to 0, correct? Can I say at time t is equal to 0, the concentration of reactant will be maximum? Absolutely. Now what is going to happen to the concentration of reactant with time? Can I say the concentration of reactant with time decreases? Absolutely. Yes. The concentration of reactant with time decreases like this. And what about the concentration of products? What about the concentration of products? I'm plotting one more curve between concentration versus time for products. This point represents time t is equal to 0. At time t is equal to 0, we know the concentration of products will be 0, and with time the concentration of products increases, as we must be knowing. Yes. Can I first of all say this curve is valid for the reactants, this curve is valid for the products. This curve is valid for the products. Yes. Which you all must be knowing, correct? Now guys, I'm going to choose one time interval right here. Let's say this point represents time t1, this point represents time t2. Similarly, in this also, let's say this point represents time t1, this point represents time t2, okay? Now people, if I want to calculate the rate of the reaction with respect to reactants in this time interval t1 to t2, how will I be doing it, yeah? Let's assume the concentration of reactant at time t1 is equal to C1, for example, yeah? The concentration of reactant at time t2 is equal to, for example, C2. As you all can see your y-axis right here, I can simply say C2 is less than C1. Yeah, C2 is less than C1, right? So people, if I want to calculate the average rate of reaction in the time interval t1 to t2, it's going to be change in the concentration of reactant right here, which is going to be change in the concentration of reactant right here, which is going to be final concentration of reactant, which is C2, minus initial concentration of reactant, which is C1, divided by time interval, which is going to be T2 minus T1 right here. T2 minus T1 right here. If I'll ask you, is the value coming out to be positive or negative? Will the value come out to be positive as negative right here? People, we know C2 is less than C1. If C2 is less than C1, the value is going to come as negative. So if I ask you what is the significance of this negative right here, this negative first of all tells us that we are calculating the average rate with respect to reactants, and this negative sign tells us that the concentration of reactant decreases with time. Yes, absolutely. Wonderful. Now people, with respect to products, if I want to calculate the average rate, we can do that. I'll be simply writing change in the concentration of products divided by time interval. Yeah. Now guys understand. Let's say at time t1, the concentration of product was, for example, something C3. Let's say at time t2, the concentration of product was, for example, C4. Yes. So people, just have a look on the y-axis. Can I simply say C4 is greater than C3? Yes. Concentration of product at time t2 is greater than the concentration of product at time t1. Yes. Now guys, I can write the average rate of reaction with respect to products. It's going to be change in the concentration of products, which is going to be final concentration of product, which is C4, minus initial concentration of product, which is C3, divided by time interval, which is going to be T2 minus T1. If I ask you, will the value come out to be positive or negative? The value is going to come as positive. What does this positive sign tell me? It simply tells me that I'm calculating the rate of reaction with respect to products, and this positive sign gives me the idea that the concentration of product increases with time. Absolutely. Yes. I hope you're clear with the average rate of reaction right here. Now comes one more important point. That's what we call as instantaneous rate of reaction. That's what we call as instantaneous rate of reaction. Okay. Before talking about instantaneous rate of reaction, guys, in physics, you would have talked about the average velocity and the instantaneous velocity. I hope you would have discussed this. Yes. Average velocity and the instantaneous velocity. Yes. How do we represent average velocity? It is going to be change in displacement divided by time interval. Yes, this is how we represent average velocity, if you remember. How do we represent the instantaneous velocity? Instantaneous velocity is the velocity at a particular instant, right? At a particular instant in a small time interval, in a very, very small time interval where delta t approaches to 0. So people, if I need to represent instantaneous velocity, can I say it's going to be like this? Limit delta t approach to 0 is going to be delta x divided by delta t, which we used to represent by dx by dt. Yes. This is how we used to represent the instantaneous velocity. This is how we used to represent the average velocity. I hope you remember that. Yeah, absolutely. Now, in the same way, we are going to represent the instantaneous rate of reaction as well. Yes, in the same way, we are going to do that. Right? Now, guys, have a look. See, I'm going to write one term right here, which is called as instantaneous rate of reaction. Instantaneous rate of reaction, which I'll be simply representing by R-INST. Yes. How do we define this instantaneous rate of reaction? So first thing, it's going to be defined as rate of reaction, or let me write it like this. It is defined as change in concentration of either reactants or products, at a particular time instant, at a particular instant, or I can say at a particular instant or a very, very small time interval, Yes, this is all basics, right? Now the point is, how do I represent it? Yes. See, guys, have a look on this. I'm going to write something like this. Instantaneous rate of reaction will be simply equal to limit change in the concentration of either reactants or products divided by time interval delta t when delta t approaches to 0. Yes, absolutely, right? I'm approaching the time interval. Towards 0. If the time interval will be approaching towards 0, then my average rate of reaction becomes equal to the instantaneous rate of reaction. Yes. Yes. Now, guys, this value is going to be simply represented by dc upon dt. Yes. This dc upon dt I'll be calling as the instantaneous rate of reaction right here. Okay. Now, guys, understand one important thing. If I'll make the concentration versus time curve right here, for example, I'm making it for the reactants, right? This is going to be the concentration versus time curve for the reactant. Yes. People, this is dc upon dt. Can I write it simply as d upon dt of c? Yes. What is this d upon dt of c? What is dc upon dt? Can I say dc upon dt is going to give me the slope of this concentration versus time curve at a point? Yeah. So can I say whenever I'll be having a concentration versus time curve, if I'll be given with a point right here, if I need to calculate the instantaneous rate of reaction at this point, I need to calculate the slope of concentration versus time curve at this point. Yeah. Now the point is, how do we calculate the slope? Yes, it's very simple. Just draw the tangent at this point. Just calculate the angle which the tangent makes with the positive x-axis in anti-clockwise direction. Let's say that angle is theta. Just take tan of this theta. This tan of this theta is going to give you the slope of this concentration versus time curve at this point A, for example. Yes, right? And whatever is going to be the slope of the curve at point A, that is going to give you the value of instantaneous rate of reaction. Yeah, very, very, very simple. Correct? Correct? Now people, I can plot one more curve for the products as well. I can plot one more curve for the products as well. This is concentration versus time. For the products, the concentration of versus time curve will be like this. Yeah, because we know the concentration increases with time for the products. Yeah, absolutely. Now guys, if I need to, for example, calculate the instantaneous rate of reaction at this point, yeah, what I'll be doing? I'll be simply calculating the slope of this curve at this point, absolutely. And how will I be doing that? I'll be drawing one tangent. Yes, I draw one tangent. I'll be calculating the angle which the tangent makes with the positive x-axis in anti-clockwise direction. Let's say that is theta. Just take the tan of this theta value. Tan of this theta value is going to give you the slope of this concentration versus time curve. And we know the slope of concentration versus time curve is what we call as instantaneous rate of reaction. Yes. Now, you would have noticed one important thing right here. See guys, the angle right here, which is theta, it is greater than 90, right? The angle right here, it is less than 90, correct? If the angle is greater than 90, can I say tan of this angle is going to be negative? So slope of the curve at this point is going to be negative. That means instantaneous rate of reaction is going to be negative. What does that mean? That means we have calculated the instantaneous rate with respect to reactants, and that negative sign signifies that the rate of reaction, that the concentration of reactant decreases with time. Yes, absolutely correct. Similarly guys, similarly over here, the angle which the tangent is making with the time axis in anti-clockwise direction, that is less than 90. So tan of this angle is going to be positive. If tan of this angle is positive, that means slope of this angle, slope of this curve at this point is positive. If slope is coming out to be positive, that means instantaneous rate of reaction is positive. And when is instantaneous rate of reaction positive? When we have calculated the instantaneous rate with respect to products, and positive sign signifies that the concentration of products with time increases. Yes, I hope this is clear to every single guy right here. Yes. Now let's come to the actual point right here. I hope this is clear to everyone. Slope of concentration versus time curve is going to give you the value of instantaneous rate of reaction. Yes, very, very, very simple. Now people, now comes the actual stuff right here, which we have to talk about in detail. Okay, from this topic the actual kinetics starts. Okay, understand. I'm going to write something. Rate of reaction from stoichiometry. Rate of reaction from stoichiometry. Understand properly what it's going to be all about. A very, very simple topic this is, but you need to understand the terminologies, and we need to see how to apply those terminologies in the questions. Yeah, understand properly guys. See, let's say I've got one balanced chemical equation as N1A plus N2B. It gives N3C plus N4D. Let's say this is one balanced chemical equation in which this N1, N2, N3 and N4 are the stoichiometric coefficients of these reactants and products respectively. Yes. Now guys, what happens to the concentration of reactants with time? Concentration of reactants with time decreases. Yes. Can I say reactants disappear with time? Absolutely. What happens to the concentration of products with time? Concentration of products increases with time. Yes. Can I say the products, they appear with time? Yes. Very, very, very simple. Now guys, I'm going to talk about few important terms right here. What is that? The first term which I'm using right here, that's what we call as rate of disappearance. Rate of disappearance. Yes. This is going to be the first term. Second term which I'll be using right here, that's what I call as the rate of appearance. Rate of appearance. So first thing which you must know right here, can I say this disappearance term will be valid only for reactants? So rate, whenever I'll be talking about the rate of disappearance, what does that mean? That means I'm talking about reactants. Yes, because we know reactants only disappear with time and products only appear with time. Yes. And whenever I'll be talking about this rate of appearance, that means we are talking about the products. Yeah. Right. Now guys, say I can use this term rate of disappearance for the reactants. For example, I'm talking about rate of disappearance of A. Rate of disappearance of A. A is my reactant, yeah. How will I be representing it mathematically? Understand. I'll be starting with the minus sign. I'll be starting with the minus sign. This minus sign will indicate that I'm talking in terms of reactants, and the concentration of reactant is decreasing with time. Yes. So first I'll be starting with minus sign, then I'll be simply writing d of A divided by dt. This minus sign signifies that the concentration of A is decreasing with time, and this dA upon dt, it is basically the change in the concentration of A in the small time interval dt. This minus dA by dt, I'll be calling it as rate of disappearance of A. Similarly, if I talk about rate of disappearance of B, B is again a reactant, so I'll be starting with minus sign, so it's going to be minus d of B divided by dt. Minus sign signifies that the concentration of B decreases with time, and this dB upon dt is the constant change in the concentration of B in the small time interval dt. This minus dB upon dt, I'll be calling this as rate of disappearance of B. Yes. Similarly, guys, let's talk about rate of appearance of C right here. How will I be representing it? Right now, I'm talking about appearance, yeah? And for appearance, I'll be using the positive sign. Yes. I'll be using the positive sign. Now I'll be simply writing change in the concentration of C in the time interval dt. Yes, this plus dC upon dt, it's going to give me the rate of appearance of C with time. Yeah. Similarly, guys, I can write something like this plus d of D upon dt. What does it signify? That means I'm talking about rate of appearance of D. That means I'm talking about rate of appearance of D, right? Very, very, very simple, okay? So people, you need to remember these two terminologies. One is called as rate of disappearance, which is valid for reactants, rate of appearance, which is valid for products. Yeah, absolutely. Now let's talk about this a bit more in detail. Let's get to know its exact things which we need in this chapter. Yeah, see guys, understand properly what I'll be saying. For example, I've got a reaction like this. N2 gas plus H2 gas. It gives, for example, NH3 gas. Yeah. Let's say this one reaction which is given to me. I'll be first of all balancing this reaction. This should be 3 times, this should be 2 times, and this is 1 right here. Yes. If I want you guys to write the rate of disappearance of N2, can you write it? Yes. N2 is the reactant. I'll be starting with a minus sign. Then I'll be writing change in the concentration of N2 in the time interval dt. Yes, I can do that, right? Similarly, guys, I can write the rate of disappearance of H2 as well. Rate of disappearance of H2 is going to be, since I'm talking about disappearance, so I'll be starting with minus sign. It's going to be change in the concentration of H2 in the time interval dt. Yes. Similarly, if I talk about the rate of appearance of NH3, what it's going to be all about? I'll be starting with the positive sign. Why? Because I'm talking about the appearance, and we know products appear with time. So this positive sign signifies that the concentration of products increases with time. So I'm going to write change in the concentration of NH3 divided by small time interval dt right here. This is how I represent rate of disappearance of reactants and products. Yeah. Number one. Number two, guys. Number two. Have a look on what I'll be doing. I'm going to take the same reaction. N1A plus N2B gives N3C plus N4D. I defined two terminologies. One was rate of appearance of one was rate of disappearance of reactant. One was rate of appearance of product. Now, guys, I'm going to write something called as a rate of reaction. Yes, in general. Remember, rate of reaction is always equal to rate of disappearance or appearance of reactants or products respectively. Right? I'm going to write the rate of reaction, which is going to be rate of disappearance or appearance of reactants or products respectively, divided by stoichiometric coefficient of the reactant or product. What does that mean? Understand. See, guys, if I want to write the rate of reaction, I can write rate of reaction either in terms of A, or I can write it in terms of B, or I can write it in terms of C, I can write it in terms of D. If I want to write the rate of reaction in terms of A, I'll be first of all writing in the numerator, I'll be writing rate of disappearance of A. And how do I write rate of disappearance of A? Minus d of A divided by dt, divided by stoichiometric coefficient of A, that is N1. So simply it is going to be minus 1 upon N1 d of A upon dt. This term is going to give me the value of the rate of reaction in terms of A. Yeah. Yes. Now, people, I can calculate the rate of reaction with respect to B as well, I'll be writing rate of disappearance of B, which is going to be minus d of B upon dt divided by stoichiometric coefficient of B, which is simply N2. So it's going to be minus 1 upon N2, change in the concentration of B divided by small time interval dt. Yes. So this term is again going to give me the rate of the reaction in terms of B. I can calculate rate of reaction in terms of C as well. I can write rate of reaction should be equal. Since C is the product, for products we do not use the term disappearance. We use the term appearance. Yes, we use the term appearance. So I'm going to write rate of appearance of C, which is plus d of C upon dt divided by stoichiometric coefficient of C, which is N3. So the value is going to be simply plus 1 upon N3 d of C divided by dt. Can I say this term again is going to give me the rate of the reaction? Yeah. Right? Similarly, guys, I can calculate the rate of reaction with respect to D as well. It's going to be plus 1 upon N4 d of D upon dt. This term is again going to give me the rate of the reaction. So can I say I'm getting the rate of reaction either in terms of A or in terms of B or in terms of C or in terms of D? And we know rate of reaction has a fixed value at a particular temperature. Every reaction has a particular rate at a particular temperature. Whatever value of rate of reaction will be coming by solving this expression, same value is going to come by solving this expression, same value is going to come by solving this expression, same value is going to come by solving this expression. So what I can conclude from here? Understand properly what I'm going to conclude from here. See, guys, I'm going to write one statement, okay? I'm going to write rate of reaction will be equal. With respect to A, it's going to be minus 1 upon N1 d of A divided by dt, which will be equal to minus 1 upon N2 d of B divided by dt, which is going to be equal to plus 1 upon N3 d of C divided by dt, which is going to be equal to plus 1 upon N4 d of D divided by dt. People, this equation which I got right here, this is what I call as differential form of rate expression. This is what I call as differential form of rate expression. Differential form of rate expression. So remember it, it's very, very important right here. Yes? Yes? So let me know in the chat box if it's clear to every single guy till here so that I can move on and talk about a few more interesting things. Let me know in the chat box if it's clear to every single guy. Yeah? Let me know in the chat box fast. Yes? Let me know in the chat box. कार्तिक यार वेट कर अभी रिवर्सिबल रिएक्शंस पे भी आएंगे, उनकी रेट भी कैलकुलेट करेंगे. वेट. Swati, I didn't take the last session of solid state, which was the defects. Yeah, defects is a theoretical topic which वो upload करूंगा बाद में कभी. ठीक है? That is one theoretical topic. Yes. Now guys, see. Now guys, understand one more important thing. This is what I call as differential form of rate expression right here. Now guys, I'm going to write one statement. See. If I'll be having a homogeneous gaseous phase reaction, I'm writing one statement, important statement right here, for a homogeneous gaseous phase reaction. For a homogeneous gaseous phase reaction carried out at constant temperature. Rate is expressed in terms of concentration as well as pressure. Yes, for a homogeneous gaseous phase reaction, rate can be expressed either in terms of concentration or in terms of pressure. And how can I justify this statement? Understand. Let's say I've got a balanced homogeneous gaseous phase reaction as N1A gas plus N2B gas. It gives, for example, N3C gas plus N4D gas. People, I'm considering the gas right here as the ideal one. If I'm considering the gas as the ideal one, can I say it should follow this equation, PV is equal to nRT? Yes. Can I say P is equal to N divided by VRT? Can I say this N by V is what we call as concentration? Can I say P is equal to concentration multiplied by R multiplied by T? Yes. So for the gas which will be at constant temperature, can I say pressure is directly proportional to concentration, which I can represent by square bracket or simply C? Yeah. Right? For gases, I can define both the terms, pressure as well as concentration. For the gases, I can define both the terms, pressure as well as concentration. Now for gases, I can define the rate either in terms of concentration or in terms of pressure. How will I be doing that? Understand? If I will write the differential rate of reaction, differential equation, what it's going to be, I'll say rate of reaction in terms of concentration, it's going to be minus 1 upon N1 d of A divided by dt. What is this d of A upon dt? dA is change in concentration of A, dt is the time interval dt. Yes, it's going to be equal to minus 1 upon N2, it's going to be d of B divided by dt. Similarly, it's going to be 1 upon N3, d of C upon dt. Similarly, it's going to be 1 upon N4, d of D upon dt. Yes? Right? Now guys, what is this A over here? This is the concentration of A. This is the concentration of A. Can I say concentration of A will be equal to partial pressure of A divided by RT? Can I say concentration of B will be equal to partial pressure of D divided by RT? Similarly, partial pressure of C divided by RT, partial pressure of D divided by RT, I can say that. So instead, guys, I can write like this, minus 1 upon N1, D of concentration of A. Instead of concentration of A, I can write D of partial pressure of A divided by RT, whole divided by dt. I can write it like this, yeah? Absolutely. It's going to come as minus 1 upon N2, d of concentration of B. Instead of concentration of B, I can write partial pressure of B divided by RT, whole divided by dt. It's going to be 1 upon N3. It's going to be d of concentration of C. Instead of concentration of C, I can write partial pressure of C divided by RT, whole divided by dt. Similarly, you can write for D as well, okay? Now people, see, R is constant, T is constant, I can take it out. So I can say minus 1 divided by N1, I can take the RT out. It's going to be D of PA divided by dt, which is going to be equal to minus 1 upon N2. I can take the RT out right here as well. It's going to be D of PB divided by dt. Yes, it's going to be equal to 1 upon N3. I'm multiplying it by RT. It's going to be D of PC divided by dt right here. Can I say, guys, this RT and this RT got cancelled out? So what I'll be left with right here, understand and remember at the same time, I can write the rate of reaction is going to be equal to minus 1 upon N1. It's going to be D of PA divided by dt, which is going to be equal to minus 1 upon N2, D of PB divided by dt, which is going to be equal to 1 upon N3, D of PC upon dt, which is going to be equal to 1 upon N4, D of P, D divided by dt. Yes, now you need to understand the terminologies. You need to understand the terminologies. What are the terminologies all about? See, D of PA. This is going to be change in the partial pressure of A in the time interval dt, change in the pressure of B in the time interval dt, change in the pressure of C in the time interval dt, change in the pressure of D in the time interval dt. This is one more way by means of which you can write the differential form for the homogeneous gaseous phase reaction at constant temperature. Let me know in the chat box if it's clear to every single guy. Let me know in the chat box fast. Let me know fast. So for a gaseous phase reaction at constant temperature, you can write this differential form either in terms of concentration or in terms of pressure. Yeah? Yes? Absolutely. Now I think it's high time to solve few questions. But before doing the questions, I told you the unit of rate of reaction is going to be mole per liter per second. Yes? Can you tell me it's one more unit in terms of ATM, in terms of atmosphere? It's going to be, see, the above term in the numerator, it's pressure, right? In the denominator, you have got time. So I can say the one more unit of rate of reaction is going to be ATM per second. Yes? Absolutely. This is going to be 1 unit. This is going to be one more unit right here. Yeah? Wonderful. Great job. Now, guys, let's try to do few questions on the concepts which we have discussed till now. Okay. The first question, is this the first question or I skipped one? Just a second, guys. Yeah, this is the first question. The very simple question which you can solve by the concepts which I gave you few minutes back. See guys, what is the equation all about? See what's the equation all about. If the concentration of H2O2 changes from 0.5 molar to 0.05 molar, that means this is the initial concentration of H2O2, this is the final concentration of H2O2 in 15 seconds. This is the time interval. This is the time interval which is given to us. Then calculate rate of reaction, rate of appearance of O2. Can't you do this question, guys? Can't you do this question? Can't you do this question? Let me know the answer in the chat box. I'm waiting for you. Let me know the answer in the chat box. I'm waiting for you. We can easily solve this one. First of all, I'll be writing the differential rate form, which is going to be equal. First, either in terms of H2O2. I'll be starting with minus sign. Change in the concentration of H2O2. Change in the concentration of H2O2 divided by time interval dt, because the stoichiometric coefficient right here is 1. Yes, which will be also equal H2O, which is a product. I'll be starting with the positive sign. Stoichiometric coefficient is 1. So d of H2O, change in the concentration of water divided by time interval dt, which is going to be equal. I'll be again starting with positive sign. O2 is the product. 1 divided by stoichiometric coefficient, that is 1 by 2. That 2 goes up. So I'll be simply writing plus 2 multiplied by change in the concentration of O2 divided by dt. Yes? Right? Now guys, what all things are given in the question? See, if the concentration of H2O2 changes from 0.5 to 0.05 molar, change in the concentration of H2O2, which I'm representing by d of H2O2, change in the concentration of H2O2 as per the equation. Final concentration minus initial concentration, 0.05 minus 0.5 divided by dt. Time interval is simply 15 seconds. Yes? Right? Right? Right guys? D of H2O2 divided by dt will come from this. Yes? What is the value which will be coming exactly? Let me know in the chat box. Let me know the exact value of it. Let me know the exact value of it. Let me know the exact value which will be coming from here. Is it coming as minus 0.03? Yeah? Okay. It's coming as minus 0.03. Right? Minus 0.03. I got the value of d of H2O2 divided by dt. Now what am I supposed to calculate? I'm supposed to calculate what? Rate of the reaction. Rate of reaction I can either calculate from this or this or this, right? So I'll be first of all using this term. I can say rate of reaction is nothing. It is minus d of H2O2 divided by dt, which is going to be equal to minus, I'm keeping as such, d of H2O2 upon dt is minus 0.03 and its units are going to be moles per liter per second. Yes. So people, you got the rate of reaction as 0.03 moles per liter per second. Yes. Now guys, you can tell me the rate of appearance of O2 as well. You can tell me the value of rate of appearance of O2 as well. How do I represent the rate of appearance of O2? How do I represent the rate of appearance of O2? You all must be knowing rate of appearance of O2 will be simply equal plus sign plus d of O2 divided by dt. That's what I'll be calling as rate of appearance of O2. Yeah. I can say something like this. Let me equate this term with this term. Can I do that? Because this term is giving me the rate of reaction. This term is also giving me the rate of reaction. I can equate the two. Yeah, I can do that. I can write something like this. Minus d of H2O2. Minus d of H2O2 divided by what? Divided by dt. Is equal to 2 times d of O2 divided by dt. Yeah. I need to calculate rate of appearance of O2. Rate of appearance of O2. See guys, take this 2 in the denominator right here. It's going to be minus 1 by 2 d of H2O2 divided by dt will be equal to plus d of O2 divided by dt. Plus d of O2 divided by dt. This plus d of O2 divided by dt, do I call this as rate of appearance of O2? Absolutely, we call this as rate of appearance of O2. So people, it's going to be simply equal to minus 1 divided by 2. D of H2O2 upon dt, we got to know that is minus 0.03. Yes, it's going to be minus 0.03. So people, you can get the value over here as 0.015, right? Moles per liter per second. This will be the rate of appearance of O2. Let me know in the chat box if it's clear to every single guy so that I can move ahead and give one more question to you. Let me know in the chat box fast. I want everyone to tell me. Is it clear? Yeah? Exactly, it's coming positive, right? That means we are talking about rate of appearance, right? Ashita, just take the video a little back. It'll be automatically a replay. Yeah, thoda dimag use kar. Yeah? Yes, wonderful. Let's move on to one more question, guys. If the rate of appearance of O2 is 0.5 moles per liter per second, then determine the rate of disappearance of N2O5. Again, a very, very simple and ordinary question, guys. You can kill this, what I'm telling you, okay? See, if the rate of appearance of O2, first of all, how do I represent rate of appearance of O2? It's going to be plus D of O2 divided by dt. If the rate of appearance of O2 is 0.5 moles per liter per second, yeah? It's given to me as per the question. We are supposed to calculate rate of disappearance of N2O5. How do I represent disappearance of N2O5? It's going to be minus D of N2O5 divided by dt. This is what I call as rate of disappearance of N2O5, which I'm supposed to calculate, yeah? Now people, use the differential equation first. Use the differential equation. Can I say rate of reaction will be equal to minus 1 upon 2 D of N2O5 divided by dt. This will be also equal to plus 1 by 2, why plus? Because I'm talking about the product, plus 1 by 2 D of N2O4 divided by dt, which will be also equal to plus D of O2 divided by dt. Yes. Which value I'm supposed to calculate? I'm supposed to calculate rate of disappearance of N2O5. Okay. Now people, can I equate this term with this term right here? I can do that. Yeah. I can equate these two, absolutely. I can get something like this. D of N2O5 divided by dt. I'm going to keep the minus sign over here, will be equal. This 2 I'm going to take in the numerator right here. It is going to be plus times 2 times D of O2 divided by dt. Do we call this term as rate of disappearance of N2O5? Yes, absolutely. It's going to be plus 2 D of O2 upon dt. D of O2 upon dt, right? It's given to me as 0.5. So 0.5. So the value is going to be 1 mole per liter per second. Can I say this is the rate of disappearance? This is the rate of disappearance of N2O5. Absolutely, yeah. Killed it, right? One more for you. Let me know the answer of this question as well. Graphical question, guys. You can easily solve this one as well, yeah. You can do it. I'm damn sure. See, guys, how this question is to be solved. For the following reaction, a curve for concentration versus time is given below. Okay, fine. Calculate the rate of reaction in the interval 5 to 15. I need to calculate the rate of reaction in this interval, 5 to 15 seconds, yeah? This is the interval in which I need to calculate rate of reaction. Understand, guys, when the time is 5 seconds, first of all, I need to identify one thing. Is this the curve for reactant or product? Can I say this? Can I say the concentration is decreasing with time? So this is the curve which will be valid for reactant, and my reactant is NH3. So this curve is valid for NH3 right here. This curve is valid for NH3 right here. Yes. When time was 5 seconds, at that time the concentration of NH3 was 0.6, which is the initial concentration of NH3, and at 15 seconds the final concentration of NH3 is 0.2 moles, yeah, per liter, right? Yes, I can say that. Now people, I can calculate the rate of reaction in terms of NH3. It's going to be minus 1 upon 2 D of NH3 upon dt. I can do that, yeah. I can do that. It's going to be minus 1 upon 2 change in the concentration of NH3, which is going to be final concentration of NH3 at 15 seconds, which is 0.2, minus initial concentration of NH3, which is 0.6, divided by time interval dt, which is going to be 15 minus 5. That means this time interval, which is 10 seconds. Yeah, time interval is 10 seconds, correct? Correct? Time interval is 10 seconds, yeah? Now, guys, it's simply going to be minus 1 upon 2. This is going to be minus 0.4 divided by 10. This will be minus plus 1 divided by 2 multiplied by 0.04, which is going to be 0.02. 0.02 moles per liter per second is going to be the rate of reaction, which we were supposed to calculate, yeah? See, guys, rate is coming positive. I told you rate is always positive, yeah? Yes. Right. One more question on a screen. You can easily kill this one as well. The question was asked in JE once. Yeah, same question. Bro, this is the English channel. I'm not supposed to talk in Hindi. Varna, meri matrabhasha Hindi hai. See, guys, how this question is to be solved. Find the relation between K1, K2 and K3, yeah? First of all, for the reaction, some parameters are given. This is the reaction which is given to me, yeah? And these are few parameters which are given to me. I'm supposed to calculate the relation between K1, K2 and K3. Yes, I can solve this one as well. Now, how will I be solving this? First of all, I can write the rate of reaction. Either in terms of N2O5, it's going to be minus d of N2O5 upon dt. Yes, this is going to be equal. In terms of NO2, it's going to be plus 1 upon 2 d of NO2 divided by dt. Yes, because this is the product, that's why I start with the positive side, which is equal to plus 1 upon stoichiometric coefficient is 1 by 2. That 1 by 2, that 2 goes up, so it becomes like this, 2 d of O2 upon dt. Yes, I can write it. Yes. Now, see. I can say rate of reaction will be equal to minus d of N2O5 upon dt. This term, yeah, its value is given to us as K1 N2O5. So instead of this term, I can write K1 multiplied by concentration of N2O5, yeah, will be equal. I'm writing something like this, 1 upon 2. D of NO2 upon dt. D of NO2 upon dt. It's given to us as K2 multiplied by concentration of N2O5. Yes, this will be equal to plus 2. D of O2 upon dt. D of O2 upon dt will be K3 multiplied by concentration of N2O5, which is given as per the equation. Can I say N2O5 got cancelled out? So I got K1 is equal to K2 divided by 2, which is equal to 2 times K3. If I multiply throughout this equation by 2, it's going to be 2 times K1 is equal to K2 is equal to 4 times K3 right here. Yes, this is going to be the relation between K1, K2 and K3 over here. Yes. Right? Right, guys? Absolutely. So people, with this, your rate of reaction is over. And this is the question which is your homework, okay? This is the question which is your homework. We are supposed to calculate the rate of reaction first in moles per liter per second, second in atm per second. Should I be solving this question right here? Or you guys are going to do it? नवीन यार, हिंदी में बात नहीं कर सकता मैं, इंग्लिश चैनल है. Durgesh, because that is 1 divided by stoichiometric coefficient. 1 divided by 1 by 2. That 2 comes up, becomes 2, yeah? Should I be solving this right here? No? You guys are going to do it? Okay, this is the homework question which you'll be doing on your own, and you'll be letting me know the answer in the comment box just after the session ends. Just let me know the answer in the comment box for both the two questions, yeah? Karthik, I have no idea, bro. You have to do that. You have to use your brains, yeah? Yes? ये homework question है. You guys are going to do this and let me know the answer in the comment box once the session ends, yeah? Right? Yes, you guys are going to do. First one, you have to calculate the rate of reaction in moles per liter per second. Second one, you have to calculate the rate of reaction in atm per second, yeah? Okay? So, do it. It's going to be your homework. Correct? People, let me tell you once again, tomorrow at 11 a.m., I am going to do the one-shot series. I'm going to start the one-shot series for the chapter electrochemistry. Yes, tomorrow at 11 a.m. to it may be till 2 p.m. Okay, I'll be finishing off the chapter electrochemistry. It's going to be a one-shot for electrochemistry, but not on this channel. It's going to be on Vedantu. It's going to be on Vedantu JEE English channel, okay? So do not miss this session at all, okay? In Vedantu JEE English channel, I'll be coming live tomorrow at 11 a.m. sharp, okay? And in that session, I'm going to start and finish the electrochemistry in 3 hours, okay? So do not miss that session on Vedantu JEE English channel tomorrow at 11 a.m., okay? Right? Yes, Ashita, chapter will be fully done. Everything will be done and dusted. If it takes me 3.5 hours to finish the chapter, I'll do that. I'll finish it off. I'll finish that chapter off, yeah? Yes, that is absolutely going to be in English. Yes, absolutely. It's an English channel, Vedantu JEE English channel, yeah? So do not miss this session at all, right? Okay? Yes, it's going to be kind of sprint, or you can call it as one shot, you can call it as marathon. You can right now go to the Vedantu JEE English channel. There you can see the thumbnail of that video, which I'm going to do tomorrow, yeah? Karthik, thermodynamics part 2 will be done on Thursday. Let me write the schedule for you once. Let me write the schedule for you once so that you can remember it. Let me tell you, tomorrow at 11 a.m. I want you guys to meet me at Vedantu JEE in English, wherein I'll be doing one shot for the chapter electrochemistry. I'll be starting and finishing the whole chapter tomorrow at 11 a.m. Correct? And people, at the same time, tomorrow at 11 p.m. on our channel, which is NEET English, yes, which is NEET Elite, I'll be continuing the chemical kinetics, right? Day after tomorrow, I'll be also doing the chemical kinetics part 3. Tomorrow it's going to be chemical kinetics part 2. Then day after tomorrow, chemical kinetics part 3. And people, on Thursday, it is going to be a one shot from the chapter thermodynamics. Yes, because we could not finish the thermodynamics chapter in the last one shot. Yes, so I'm going to do the part 2 of thermodynamics, in which I'll be talking about the first law of thermodynamics, enthalpy, the relation between delta H, delta U, heats of reactions, Gibbs free energy, and entropy. Okay, right? So on Thursday, and the timing is going to be 6 p.m. 6 p.m. on NEET Elite. Yeah, 6 p.m. on NEET Elite channel. So do not forget to attend this session as well, right? Okay. And I'll be sharing the link at the same time on my Instagram handle, which is WASSIMBHAT, wherein you can see everything, okay? I'll be sharing everything on my personal Instagram, right? कोई नहीं कार्तिक, आप परसों आप school से आके देख लेना वो, no issues, yeah? All right, so people, with this, let's end today's discussion right here. Tomorrow at 11 a.m. I'll see you, okay? And tomorrow we'll do the one shot on electrochemistry. And tomorrow only at 11 p.m. on NEET Elite channel, we are going to do the chemical kinetics part 2. And from now onwards, the sessions are going to be regular. I know in the last week, I could not attend these sessions regularly because of my health issues, throat issues, and all, as you all must be knowing, yeah? Okay, but from tomorrow, it's going to be regular. This week, we are going to finish the kinetics. And in the next week, we are going to start the GOC, and solutions will do parallelly, okay? Right? Okay, so people, it was really a nice, energetic session. I felt that, yeah. Yes, Ashita, now I'm all fine. Thank God, yeah. So I'll see you guys tomorrow at 11 a.m. on Vedantu JEE English channel. Till then, you guys take care. Bye-bye. God bless you all. Love you all. Good night. Sweet dreams. Take care. Bye. Take care, guys. Bye.